So our last speaker for today is Xin Fu, who's here from BIMSA. She's going to tell us about homotopy rigidity for quasitoric manifolds over products of D simplicity.
Okay, thanks, Stephen, for introducing me. And I would like to thank the organizers to offer me an opportunity to speak. Today, I would like to report recent progress jointly with Larry Johnbeck and Stephen Terrell. So let me start with our main result. So we considered quasitoric manifolds over a product of D simplices, and so we assuming M and N are two n-dimensional quasitoric manifolds. So explicitly, that means N equals to the dimension of the polytope, which is DL. So in this case, and we use the curly P to denote the set of all the prime numbers that is not greater than n minus d plus 1. So our result is the following. So suppose we consider two such kind of like quasitoric manifolds. Suppose their integral coefficient rings are isomorphic. Then we can show that these two quasitoric manifolds, M and N, they are homotopy equivalents after localizing away the prime numbers inside this set P. So in this talk, I will give you the definitions of the concepts involved in this result, and also talk about the ideas in proving this statement. So first of all, let me introduce moment angle manifold from a simple polytope. I know throughout this workshop, we talk about moment angle complexes as a special kind of like polyhedral product. But in this talk, I would like to, or I prefer to think of moment angle complex arising from simple polytopes as a pullback square, so appearing in some pullback square. To fixed notation, so I'm using Pn. N is always to be the dimension of the simple polytope, and in this case, we can always write Pn as a set of points in n-dimensional Euclidean space, such that these inequalities are satisfied. So, so here, a construction due to Boucher-Turbo, Panov, and Ray shows that we can always embed an n-dimensional simple polytope into a non-negative n-dimensional Euclidean space, just sending every point in this n-dimensional simple polytope to the number appearing in the left-hand side of this inequality. So that's the bottom arrow embedding Pn into Rm. Okay, so the right-hand side vertical arrow mu is the moment map from Cm going to Rm, so non-negative coordinates. So in this case, we can define the moment angle manifold as the pullback of these two maps. So on the other hand, we can always write Cm as a quotient space of this non-negative orthant M Euclidean space times a torus modulo some equivalent relations. So this gives the moment angle manifold as a quotient space of n-dimensional simple polytope and m-dimensional torus. So I will give you an example to show how this quotient space looks like. So for example, if we think of the one-dimensional simple polytope, which is just an interval from, let's say, from 0 to 1. So, so when P is an interval, so in this case, the number of the codimensional 1 faces are just the two endpoints. So the vertices of this interval. So M will be equals to 2. So in this case, so M always refers to the codimensional 1 faces of this simple polytope. So before we take the quotient, So we have P times T2. So means to every point in this polytope, we attach to a two-dimensional torus. So this is just this product space. Then we do the quotient. So the quotient, the recipe or the rule defining the quotient relies on the point lying in the P, relies on the codimensional of the, so every point in will contain in a relative interior of some face. So every face will have a codimension in this simple polytope. So when we think of the point lies in a codimensional K face, let's say the codimension of this face is K. So in this case, we'll quotient out a K-dimensional subtorus inside of this Tm. So in the moment angle complex case, this K-dimensional subtorus will always be the coordinate circle given by this Tm. So for example, if we think of the endpoint, the vertex, let's say the left vertex of this interval 0. So in that case, so originally before we take in the quotient, it will be a two-dimensional circle. So in the quotient space, we will quotient out the first coordinate circle. So that means the remaining part to the endpoint 0, we will only have one circle remaining in this quotient space. And similarly to the endpoint 1. So in that case, we will quotient out the second copy of this coordinate circle. So in this case, we attaching to this vertex, we only again remaining just one-dimensional circle. But for the point lies inside this interior of this interval, because the codimension of this point face will be 0, so there's no torus quotient out. So to each the point in the interior of this simple polytope, we will have the whole two-dimensional torus. So in the end, the resulted quotient space will be the join of S1 and S1, which is S3. So this is a different way to look at to define the moment angle manifold. Is this clear? So a second definition of the space I want to introduce is called the quasitoric manifold. So the quasitoric manifold, from the definition in a geometric point of view, is we look at compact manifold. Suppose it is 2n-dimensional, and on this manifold, globally, there's an n-dimensional torus acting on this manifold. And this torus action, Tn, acts on M, will satisfy some so-called locally standard torus action, such that the quotient orbit space will be an n-dimensional simple polytope. So that's from a geometric point of view, we define a quasitoric manifold. So here is an example. So think about our two-dimensional sphere, and think about the S1 acts on this two-dimensional sphere just rotating along this equator circle. So this is the S1 action on this S2. So locally standard torus action means to each point, there's a local charge, such that if we restrict to this torus action to this local area, it will becomes the standard Tn action acts on this Cn. Okay, so in this S2 case, so there are local charges given by just removing the north pole or the south pole. So in that case, if we look at from the top to the two-dimensional sphere, we can get the S1 action acts on the local charge is just rotating along the original. So this is a locally standard action. So S2 equipped with this S1 action is a quasitoric manifold. Another way of defining a quasitoric manifold is by construction. So similarly to what we see before, what we saw in defining a moment angle manifold, Here we also think of the simple polytope product, take the product with another n-dimensional torus. So here n equals to the dimension of this polytope. So this is different to when we're defining the moment angle manifold. So moment angle manifold, the dimension of the torus equals to the dimension of the codimensional number of the codimensional one faces. But here, the torus will be n-dimensional, which is agree with the dimension of this simple polytope. To defining this equivalent or the quotient relation appears in this quotient space, we need an extra delta, which is a function from f1 dot 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 to fm. Is the set of all the codimensional one faces of this simple polytope. And we call it a characteristic function, means whenever the intersection of all the facets is not an empty set, the image of those vectors will form part of a basis of this n-dimensional lattice. So that's what we call an n-dimensional, what we call a characteristic function. So in this case, we form an equivalent relation, which is related to this lambda characteristic function. Again, in a similar pattern as we defining a moment angle manifold, we need to consider the first coordinate x lies in which face, relative interior of the face of this polytope, and we need to quotient out certain codimensional k face will be corresponding to a k-dimensional subtorus in this Tn. So in this quotient relation, we will quotient out this k-dimensional subtorus. How do we determine this k-dimensional subtorus? It will be given by the vectors that comes from the image of this lambda function, which span in this k-dimensional torus in this Tn. So here is an example. Again, I'm using the P to be an interval from 0 to 1. So in this case, n is 1. So before we take the quotient, we are taking the product of this one-dimensional simple polytope with a one-dimensional torus, which is just an S1. So the space before taking the quotient is just a cylinder, right? This is just a cylinder. Then again, we look at the codimensional one face, which are just these two endpoints, and the characteristic function sending 0 to 1, and another one, another ending point also send to 1, because we only have this one-dimensional lattice, which is just the integers. So in this case, to this left endpoint, because the one will span a one-dimensional circle in S1. So that means the left circle S1 will be quotient out to a point. And similarly to this right side endpoint, so this S1 will also be quotient out to a point. And for the other points inside the interior of this interval, we do not have any quotient relation. So in this case, the resulting quotient space will be S2. Is this clear? So here is another example. If we think of the pentagon, which is a two-dimensional simple polytope. So before we take quotient, again, it is a product of P2 times two-dimensional torus. And then to every vertex, they are codimension 2 face. So in that case, we will quotient out all the two-dimensional torus. And to every point lies in the interior of the edge, they are codimensional 1. They lies in a codimensional 1 face. So that means we quotient out one-dimensional circle inside this T2. So this one-dimensional circle is spanned by this characteristic vector associated to this codimension 1 face. So the remaining part will become, again, T2 quotient out one-dimensional circle will be still up to homotopy equivalence, it is again another S1. So similarly, we can do the same process to each of the edge, and for the point lies inside the interior of the polytope. So it is co-dimensional 0. So there's no quotient happening inside this interior of this polytope. So every point inside the polytope will attach to the two-dimensional torus. So this is the picture for four-dimensional toric manifold. Okay. So there are non-trivial examples of quasitoric manifold. For example, a Bott manifold, which is appears in a sequence of manifolds. So we're starting with a point. So we do the projectivization of a trivial line bundle and a direct sum of trivial line bundle of another line bundle. So then iterate this process. So in the end, we get an n-stage manifold. So each of the n-stage manifold is a Bott manifold. So this is a non-trivial example of our quasitoric manifold, and the associated polytope will be an n-dimensional cube. And we can also generalize this construction to instead of thinking of one trivial line bundle and another maybe arbitrary line bundle. So we can think of one trivial line bundle together with nk minus 1 line bundles, then do the projectivization of this Whitney direct sum. So in this case, the resulted n-stage manifold will be called a generalized Bott manifold, and the associated simple polytope to this generalized Bott manifold will be a product of simplices. The simplices dimension for these simplices might not be the same one. Okay. To compute the cohomology, so remember we have this M is a quasitoric manifold defined as a P times Tn modulo some equivalent relation. So there's a torus action X on this manifold given by the torus action acting on this torus factor. So in this case, we can consider the Brill fibration from this Tn action on this M. So we end up with a homotopy fibration. So this is the Brill construction of this quasitoric manifold. Then we project down to the Klein-Phi space of Tn. A result due to Davis-Yanskevich showing that the cohomology of the fiber, which is the cohomology of the M, will be isomorphic to the E2 term of this Eilenberg-Mohr spectral sequence. And moreover, we can compute this total to be the equivalent cohomology ring of this quasitoric manifold modular, the ideal generated by the image of induced map on the cohomology, which we do not require the zero cohomology. So you can also compute the equivalent cohomology of this quasitoric manifold turns out to be isomorphic to the Stanley-Ranzner ring associated, sorry, this should be P, associated to this simple polytope. And the image of this element can be is represented by some linear relations inside this ZKP. So this is the cohomology formula for computing quasitoric manifold. What we are interested in understanding an open problem in toric topology, which was asked by Masuda and Su in around 2008, saying that given two quasitoric manifolds or two toric manifolds, let's say M and M prime, suppose their integral cohomology rings are isomorphic, can we say they are diffeomorphic or homeomorphic to each other? So that's the rigidity problem in toric topology. So it sounds like the question sounds like quite ambitious, but we don't know any counterexamples after the question was asked. There are supportive cases. So for example, if we think of the four-dimensional quasitoric manifolds, that means the associated symbol polytope is just any polygon. So in this case, we can use the cohomology formula given by DJ and the Friedman's classification of four-dimensional manifolds. We can get four-dimensional quasitoric manifolds satisfy this cohomology rigidity property. Result due to Butcher-Turbo and his collaborators considered not every six-dimensional quasitoric manifold, but six-dimensional quasitoric manifolds associated to Pogorelov class. So basically, that means the associated simple polytope contains no triangles, no squares. So in that case, we know this class of manifolds also satisfy this property. Recently, Choi, Huang, and Jiang, they showed that both manifolds are also they are also satisfy this property, and similarly, quasitoric manifolds over three-dimensional cube due to Hasse, or quasitoric manifolds over a product of two simplices. This is also satisfy they are also affirmative cases to this problem. So we modify this question instead of answering whether they are homeomorphism or diffeomorphism. We think of a homotopy, a weaker version, or a homotopy version of this problem, asking, given two quasitoric manifold, let's say M and N, suppose their cohomology ring are isomorphic to each other, can we say they are homotopy equivalents? So that's so there are results that are relevant to this question. For instance, Hasse and Kishimoto shows that for quasitoric manifold with dimension less than 2p squared minus 4, so here p is a prime number, and in this case, cohomology ring isomorphism can imply they are homotopy equivalents after p localization, and we suspend the space many times as possible. So this is involving the suspension, and with Larry and Zhongbai, we think we considered four-dimensional torical orbifolds that has no two torsion. So you can think of torical orbifolds are analog of orbifold version of quasitoric manifold, and we do not consider, we exclude the case that the space having two torsion. So in this case, we can show that the cohomology ring isomorphism will imply the homotopy equivalence between those spaces. So recently, we with Larry, Zhongbai, and Stephen, we think about the quasitoric manifolds over a product of d-dimensional simplices. So this class of quasitoric manifolds include the Bott manifolds and a certain generalized Bott manifold. So in this case, we prove that the integral cohomology ring isomorphism will imply the homotopy equivalence after certain localization. So after inverting several prime numbers. So for the remaining of the talk, I would like to talk about the idea in the proof. So first of all, from the cohomology of the quasitoric manifold, we understand there is a cellular structure for quasitoric manifold that consists of only even dimensional cells. So that means the zero skeleton of M because it is simply connected, so it is homotopy to a point. And the two skeleton will be a wedge of two-dimensional spheres. And again, this is 2n dimensional, so the 2n skeleton of this M will be M itself. And for each of the 2k plus 2 skeleton, we have certain attaching map attaching 2k plus 2 cells on this 2k plus 1 skeleton of M, because M only consists of even dimensional cells, so the 2k plus 1 skeleton will be equals to the 2k skeleton. So we can write a cofibration sequence for appearing arising from this quasitoric manifold. Our idea is to show each the 2k skeleton under the assumption of this main result. We will have this homotopy equivalence after localization. So we divided into two cases. So first of all, we consider the k equals to d. So d is the dimension of these simplices. And the second case is when the k is greater than d. So that's the idea for proving the result. So let's first say when k is d. So when k is d, we consider the fibration of M. So what's this one? So this is because the quasitoric manifold can be understood as a quotient space from the moment angle manifold given by a free torus action. So the freeness can be deduced or proved by using the definition of the characteristic function. So because it is a free action acts on M, so we can classify this map going to be the classified space of BTM minus N. So we end up a fibration from the whose fiber will be the associated moment angle manifold. So because we are considered the polytope, which is the product of D simplices, so the associated moment angle manifold is a product of 2D plus 1 spheres. So the connectivity of this fiber is 2D. So roughly speaking, we can understand the map delta from M to BTM minus N at a certain lower degree. So the fiber of this delta could be just a contractible space because the connectivity of this fiber is 2D. Or to make it formal, we can apply Blaker and Massey theorem to show the result. But roughly intuitively thinking, because the connectivity of the fiber is higher, so we can understand at a certain lower degree of this map, the fiber would be contractible. So that gives a homotopy equivalence when we restrict to the delta to only 2D skeleton. So that's how we end up induced map restricting to the 2D skeleton. And this same fibration also applies to the quasitoric manifold for N as well. So in this case, we can consider the composition from delta 2D, so delta 2D and delta prime 2D. So delta prime 2D denotes the same map for the N instead of like M. And the arrow appears in the middle is induced from the assumption by when we assuming the cohomology are isomorphic. So there will be an isomorphism of degree 2M and degree 2N. So it will induce an isomorphism from the BT M minus N goes to BT minus N because they are classifying map of the degree 2 of this cohomology of quasitoric manifold. So that means this map will also be a homotopy equivalence. So each of the map will be a homotopy equivalence so that the composition will be a homotopy equivalence. So that's for the K equals to D case. Okay. Any questions so far? So for the K greater than D case, we use lemma, useful lemma. So we may generalize thinking a CW complex which consists of even dimensional cells, or of course, connected CW complex. So we can define a homomorphism. So from the 2K plus 2 homology groups of X, so we can understand these homology groups to be the cellular homology. So because X consists of even dimensional cells, so each of the cell will contribute to a homology class in the cellular homology groups. Okay, so we understand this one as a cellular homology of X, and the target space of this homomorphism Gx is the homotopy groups of 2K skeleton of X at degree 2K plus 1. So if we take a 2K plus 2 dimensional cell of X, so it will give us a homology class inside the homology groups of X, and think about the boundary of this cell, which is 2K plus 1 dimension. So think about the attaching map from this cell to the 2K skeleton of this X. So take the homotopy class of this attaching map. So this is the image for this 2K plus 2 cell of our CW complex. Okay. So we can show this is a well-defined group homomorphism. And we can also show that this group homomorphism is natural with respect to a continuous map between two CW complexes that consist of even dimensional cells only. So I'm using H star to denote the induced map on the homology groups, and using the H2K, the subscript H2K, to denote the induced map on the 2K skeleton. So given any continuous map, we always have this commutative diagram. So the top arrow is Gx, the bottom horizontal arrow is Gy. The map defined similarly for another CW complexes consisting of even dimensional cells. For our quasitoric manifold over a product of similaces, so when K is greater than D, so K refers to the K appearing in defining this group homomorphism. So we can show the map Gm. I mean, M, the subscript M means we consider the X to be the quasitoric manifold M. So we can show that this map Gm is indeed an isomorphism after localizing those prime numbers in the set of curly P appearing in here. So that's the crucial part in the statement, improving the result. Okay, now we getting back to our case when K greater or equals to D. So we use a inductive process. So remember we consider two quasitoric manifolds M and N over the product of these similaces, and we know Gm and Gn, they are isomorphism after after the appropriate localization. And suppose we have shown for the K equals to D, there's a homotopy equivalence between the 2K skeleton to the 2K skeleton over here. So that means on this right-hand vertical arrow, this is an isomorphism between the homotopy groups, or isomorphism after appropriate localization. Because Gm and Gn, this is also an isomorphism after localization. So that means we can get a map which is also an isomorphism after localization from the cellular homology groups of M to the cellular homology groups of N. okay? And moreover, this map can be kind of like a geometric geometric realized in terms like each of the cell. Because the homology groups corresponding to the cells of this structure, cellular structure of this M, so we can get a map mapping the 2K plus 2 cells of a map goes to the 2K plus 2 cells of the N. So such that the attachment map for the M and the attachment map for the N, and this right-hand side is the inductive process, homotopy equivalence we proved after localization. And the commutativity of this part will imply a homotopy commutativity on the level of these spaces. And the horizontal maps denotes the attachment map for the 2K plus 2 cells of M and N respectively. And all the vertical arrows, they are homotopy equivalence after localization. That means there will be an homotopy equivalence between the induced cofiber of this attachment map. So this shows the homotopy equivalence between the 2K plus 2 skeleton of M and the 2K plus 2 skeleton of N. So that's, stop here, that's the end of my talk.